All right, if y'all don't mind, I'm gonna give that brief intro again so that we'll have what this section's about. The addition and subtraction formulas help us find the exact values for angles that we don't have memorized on the unit circle. So for example, if we have sine of 30 degrees memorized and sine of 45 degrees memorized, maybe we just add those two values to get the sine of 75 degrees. Well, it turns out to be not quite that simple, but we are going to have some formulas for using the trigonometric values of angles we do have memorized to find the values of trigonometric functions that we don't have memorized on the unit circle. And the first thing in this section is the idea of cofunctions. You already know that whatever cosine is at 30 degrees, sine's going to be the same thing at 60 degrees. Sine and cosine are cofunctions of each other. Tangent and cotangent are cofunctions of each other. That means whatever cotangent is at some angle, tangent is going to be that same value 90 degrees earlier or 90 degrees later. Now, this is expressed in radians rather than degrees. That doesn't matter. Secant and cosecant are cofunctions of each other. So if I ask you to find a trigonometric value as a cofunction of a complementary angle, if I give you an angle in degrees, you're going to just subtract that angle from 90 degrees. If I give you an angle in radians, you're going to subtract that from what? What's equivalent to 90 degrees?
Pi over 2.
I'm sorry, what?
Pi over 2.
Yes, pi over 2. So we've already done the A part here. The tangent of 37 degrees 50 minutes is the same value as the cotangent of 52 degrees 10 minutes. I'm not even going to do the B part because it's the exact same thing. The C part, cosine is the cofunction of sine. So whatever cosine is at pi over 3, sine's going to be the same thing at pi over 2 minus pi over 3. And that's 3/6 minus 2/6 is 1/6 pi. And this is actually what I was talking about here. Since pi over 6 is 30 degrees, whatever sine is at 30 degrees, cosine is going to be the same thing at 60 degrees. The D part's the same thing, except for it's in decimal degrees rather than degrees, minutes, seconds. What about number 4? What are the units on these two angles? Tangent of square root of 2. Is that square root of 2 degrees or square root of 2 radians?
2 radians.
Yeah, if it doesn't have the degree symbol, it's radians. So the tangent of the real number square root of 2 is the same thing as the tangent of square root of 2 radians. So to find the cofunction, you would say tangent is the cofunction of cotangent. Whatever tangent is at square root of 2, cotangent's going to be the same thing at pi over 2 minus square root of 2. And if you want an exact answer, that's the best we can do there. I don't want a decimal approximation. I want a cofunction of a complementary angle, and pi over 2 minus square root of 2 is the complement of square root of 2. For the D part, secant is the cofunction of cosecant. Whatever secant is at 1.2, cosecant is the same thing at pi over 2 minus 1.2. So that's all there is to cofunctions. Now, the addition and subtraction formulas, it would be awfully nice if what I said a minute ago if we knew that, for example, the sine of 75 degrees is the same thing as the sine of 30 degrees plus the sine of 45 degrees, that would be way easier to memorize than these addition and subtraction formulas. Unfortunately, that's not true. And that's why we have to have addition and subtraction formulas if we're looking for exact trigonometric values of angles that we don't have memorized on the unit circle. As long as we can write that angle as the sum or the difference of two angles that we have memorized, then we can use these addition and subtraction formulas. In 6.4, we'll have double angle formulas and half angle formulas for the same thing. For example, if we want the sine of a 15-degree angle, we can say, well, that's half of a 30-degree angle, and use a half angle formula. But that's next time. All right, there is no point in you memorizing these formulas. I don't have them memorized myself. If I need them, I look them up. And I need them very rarely in calculus, but pre-calculus gives me just enough exposure to them so that if I am in a situation in calculus where I need to find the sine of 75 degrees and I need the exact value rather than a decimal approximation, I know these formulas exist and I can Google them or I can look them up in the book. Since the last test will be open book, you'll have all those formulas you can refer to. All right, so let's see how to use them. Number 6, the B part is asking us to find the sine of 11/12 pi. And 11/12 pi is not one of the angles we have memorized on the unit circle. We don't have our 12ths memorized. So somebody just happened to notice that 11/12 is the same thing as 2/3 plus 1/4. This would be 8/12. This would be 3/12, and 8/12 plus 3/12 is this 11/12. So it may seem like these should be the same, should have the same values, but they don't. If you find the sine of 2 pi over 3, 2/3 pi, this is 1/6263646. What is sine right there? What's the value of sine when you're only 30 degrees from the y-axis? This is the ordered pair 0, 1. So, excuse me, this is the ordered pair -1/2, comma, square root of 3 over 2. So what is the sine of 2/3 pi? Miss Carly? I can't hear it. Excuse me, I can't hear anybody. Are y'all still there?
Yeah. Is it square root of 3 over 2?
Yeah, absolutely. Miss Carly, Miss Kelsey, why were you quiet on that one? Is there anything bugging you? Miss Carly, can you hear me?
Oh, she just sent a message in chat. I don't think she can talk right now.
Oh, okay, okay. Miss Kelsey, can you hear me? Well, Evan, it may be just you and me. I don't know.
Answer all the questions.
Yeah. Did Kelsey say anything in a chat?
Yeah, she said her volume isn't working right now, but she's here.
Okay. All right. Well, shoot. You're right. The sine of 2/3 pi is square root of 3 over 2. And the sine of pi over 4 is square root of 2 over 2. So if we wanted an exact value for the sum of these two angles, all we could do is write it as a single fraction, square root of 3 plus square root of 2 over 2, and that's the exact value for the sine of 2/3 pi plus the sine of pi over 4. Now, if it were true that to find the sine of some angle we don't have memorized, we can just add the sines of the two values that we do have memorized, then these two answers would be the same. But I know that I can't distribute sine through a sum, just like I can't distribute an exponent through a sum. If I have a plus b squared, I can't just square the a and square the b. And I have to remember, excuse me, the same thing is true with trigonometric functions and with logarithms. You can't distribute functions like you can distribute constants. So to find the sine of 11/12 pi, we do need to know that 11/12 pi is 2/3 pi plus pi over 4. But then we have to use the addition formula for sine. If I call 2/3 pi my u and pi over 4 my v, then the sine of u plus v is the sine of u, that's the sine of 2/3 pi, times the cosine of this v, pi over 4, plus the cosine of u, which is my 2/3 pi, times the sine of v, which is my pi over 4. Sine of 2/3 pi is square root of 3 over 2. Cosine of pi over 4 is square root of 2 over 2. Cosine of 2/3 pi, the x value at 2/3 pi is -1/2. And sine of pi over 4 is square root of 2 over 2. I really didn't leave myself enough room right there. So I'm going to go right above it and say that is square root of 6 over 4. The second term would be minus square root of 2 over 4. So when I wrote that as a single fraction, it would be square root of 6 minus square root of 2 over 4. And if we found a decimal approximation of this and a decimal approximation of that, they're not the same thing. And that proves that you can't just find a trigonometric function of a sum by adding the trigonometric function of the two parts. Also, I can punch the sine of 11/12 pi on my calculator and get a decimal approximation. Let me show you. I'm going to put my calculator in radians and say 11/12 pi. I have the fabulous backwards calculator. 11/12 times pi. And then the sine of that is about 0.26. I could punch that on the calculator and it would be about 0.26 as well. All right, now, excuse me, on number 6, I'm not sure that I would have thought, hey, 11/12 is just 2/3 plus 1/4. That hint was given to me in the book. Otherwise, it may have taken me a while to find two angles that I could add, two angles that I have memorized that I could add together to get 11/12. I think I eventually would have come up with it, but not very quickly. On the B part, we're not, or on number 8, we're not given that hint. So we do have to think of two angles that either add or subtract, two angles that we have memorized on the unit circle that either add or subtract to give us 195 degrees. And all of us could come up with a different way to split that 195. Does any way occur to you, Evan, any way that we could write 195 as the sum or difference of two angles we have memorized? First, I was thinking 180 plus 15, but that doesn't help because we don't have the trigonometric functions of a 15-degree angle memorized. So it's going to have to be something else. Mr. Evan, have you thought of any two angles that we have memorized that either add or subtract to give us 195?
Sorry, my mic wouldn't unmute. Not yet.
Okay. Well, let me tell you that I've been counting by 45s for a long time in my life, long enough to know that 45 times 3 is 135. So my second quadrant quarter pi is
Also,
135 degrees.
Also, Kelsey said 135 and 60.
Oh, yay. Okay, so Kelsey, you and I, great minds think alike. That is not the only way that we could split the 195. It's just the first way that occurred to me and to Kelsey. So I'm going to go ahead and do that and say cosine of 195 degrees is cosine of 135 degrees plus 60 degrees. Now I can't just take the cosine of 135 and the cosine in 60 and add those two values together, but I can use the addition formula for cosine. If I let 135 degrees be my u and 60 degrees be my v, then the addition formula for cosine would say cosine of u, which is 135 degrees, times the cosine of v, which is 60 degrees, minus the sine of u, which is 135 degrees, times the sine of v, which is 60 degrees. Since 135 degrees is one of my quarter pies, specifically it's my quarter pi in the second quadrant, what is cosine of 135 degrees?
Negative square root of 2 over 2.
Square root of 2 over 2 because it's a quarter pi, and negative because it's the x value in the second quadrant. And then what is the cosine of 60 degrees?
One half.
Yep. Then the sine of 135 degrees, again, it's a quarter pi in the second quadrant. So sine would be positive square root of 2 over 2. And what is sine of 60 degrees?
Square root of 3 over 2.
Right. So when I multiply the fractions in each term and combine to get a common denominator to add them, that's just negative square root of 2 minus square root of 6 over 4. If I'm not working for NASA, then punching cosine of 195 degrees on my calculator, getting a decimal approximation will probably be just fine. But if I am working for NASA or any other organization that requires exact values, then we have just found the exact value for an angle we don't have memorized on the unit circle. All right, let's see what's on the back here. Okay. On the previous page, we were taking a single angle and splitting it into two angles. On 12 and 16, we're taking two angles and putting it back together as one. So to do that, I need to find one of my formulas on the front page that has cosine, cosine minus sine, sine. On the previous page, which one of these four have a cosine, cosine minus sine, sine?
The second one.
Yeah, the one we just used. That's the addition formula for cosine. So just going to make a note here. This is the addition formula for cosine. And that allows me to put these back together as the cosine of what?
I'm sorry, what'd you say?
If we put this back as cosine of a single angle, what would that single angle be? I could make it multiple choice. I could say it could be 19 degrees, or it could be 31 degrees, or it could be duck. Which one is it?
31.
Yeah, because this is the addition formula for cosine. If we worked backwards with this cosine of 31 degrees and did the same thing we did on the previous problem, we would say 31 degrees is 6 degrees plus 25 degrees. And then we would use the addition formula for cosine to break that into exactly this. Now, I can not justify as well the purpose of doing this, because if we were trying to find exact value for cosine of 31 degrees, this wouldn't be helpful because we don't have exact values for any for a 6-degree angle or a 25-degree angle. But if I have my formulas in front of me, I can recognize that's the addition formula, and so that's cosine of 6 degrees plus 25 degrees. Now, there's one thing that's a little bit strange about number 16, in that here I have a -5, but here I have a +5. Here I have a +2, here I have a -2. At least in number 12, both terms had a 6-degree angle and both terms had a 25-degree angle. That's not the case here. Well, this goes back to something that I told you a long time ago that you don't have to memorize. That is the formula for negatives. And the reason I said that you don't need to memorize the formula for negatives, let's say I went 5, I know that these are in radians, but let's just play like they're in degrees for a second to make a point. If I went 5 degrees counterclockwise, that's my positive angle. If I went 5 degrees clockwise, that would be my negative angle. If I've gone the same distance clockwise or counterclockwise, what's the same in these two ordered pairs? Are the x's the same or are the y's the same?
The x's.
The x's are the same. This might be some x, y, and this would be x negative y if I'd gone the same distance in the opposite direction. So what stays the same whether you're going clockwise or counterclockwise? Is it sine or cosine that stays the same?
Cosine?
Cosine, because your x's are the same here. In other words, in the place of cosine of positive 5, I could put cosine of negative 5 without changing the problem. And instead of cosine of positive 2, I could put cosine of negative 2 without changing the problem. If I did that, then I would have negative 5 in both terms and negative 2 in both terms. If I want to identify what u and v are, then I need the same u in both terms and the same v in both terms. The only thing that allowed me to do that was the fact that cosine of negative 2 is the same as cosine of positive 2. And cosine of negative 5 is the same as cosine of positive 5. Now, which one of my formulas says sine, cosine, plus cosine, sine? Sine, cosine, plus cosine, sine.
That's addition sine.
Yeah.
Sine.
And you said that well. That's the addition formula for sine. So if I can identify u and v, then I can put this whole right-hand side back together as the sine of u plus v. That does not look right. All of a sudden, it's bad when your math teacher can't spell addition. Oh my gosh, it's one of those times. It's one of those times nothing looks right. Okay, that's right, but I just had a weird moment. Okay, since this is the formula for the addition formula for sine, then all of this can be put back together as the sine of negative 5 plus negative 2, or the sine of negative 7. Miss Kelsey, can you talk yet? Nope. Miss Carly? Evan, it's still just you and me, buddy. Thanks for hanging with me. All right, number 18 says if cosine of alpha is 24 over 25 and sine alpha is negative, find the exact value of cosine alpha plus pi over 6. Well, how am I supposed to find the cosine of alpha plus pi over 6 if I don't know what alpha is? I don't know what alpha is. I know what cosine of alpha is, and I know that sine of alpha is negative, but I don't have any angle on the unit circle whose x-coordinate, I should say, any angle that I have memorized on the unit circle whose cosine is 24 over 25. So I don't know what alpha is. I can't find what alpha is, but I'm supposed to find cosine of alpha plus pi over 6.
You could.
I'm sorry, what?
I was just going to say you could use cosine addition formula and just replace cosine alpha with 24 over 25.
Let's see. Cosine, the addition formula for cosine. Well, the only problem, that was a great idea, Evan, except for to use the addition formula, I would have to know what sine of alpha is, and I don't know what sine of alpha is. I just know that it is negative. So think about something, we've had problems like these earlier that said, in what quadrant does alpha lie? If cosine of alpha is positive, in what two quadrants is the x coordinate positive?
1 and 4.
1 and 4. And in what two quadrants is sine negative?
3 and 4.
So based on the fact that we know both of these things are true, in what quadrant does alpha have to lie?
4.
Yep. And even though I don't know exactly what alpha is, I know it's a fourth quadrant angle. So I'm just going to draw me a fourth quadrant angle, and I don't know whether to make it closer to the x-axis or closer to the y-axis. I'm just going to put it here and say, here's my angle alpha. And if I raise a vertical line up to the x-axis, then I can label all three sides of this triangle based on the fact that I know cosine of alpha is 24 over 25. Using the words opposite, adjacent, and or hypotenuse, what does cosine give you? The definition of cosine in terms of opposite, adjacent, or hypotenuse.
My mic wasn't unmuting again. Cosine is adjacent over hypotenuse.
All right, that means 24 is the side adjacent to alpha, and 25 is the hypotenuse. How could I find this vertical leg?
Pythagorean theorem.
Yep. 25 squared is 625. 24 squared is, I think, 625, 576. 625 minus 576. I think that's 49, but I'm going to double check.
It is.
Okay, so the square root of 49 is 7. 7, 24, 25 is a Pythagorean triple. All right, Evan, going back to your idea a minute ago, this looks like this would require the addition formula for cosine. The only reason we couldn't use it to begin with is the fact that that formula was going to require sine of alpha. Well, now I can tell you what sine of alpha is. What is sine of alpha?
That would be 7 over 25.
Perfect. So using the addition formula for cosine, that's cosine, cosine minus sine, sine. Cosine, cosine minus sine, sine. All I have to do now is plug in some numbers. Cosine of alpha was given to me. That's 24 over 25. Pi over 6 is an angle I have memorized on the unit circle. Cosine of pi over 6 is square root of 3 over 2. And then using this triangle, we found out that sine of alpha is 7/24, and sine of pi over 6 is a half. Typo. That was supposed to be a 25. 7/25ths, I think is what I said, but I wrote 7/24ths. Our common denominator would be 50, and our numerator would be 24 square root of 3 minus 7. So that over 50 is the cosine of alpha plus pi over 6 without ever knowing exactly what alpha is. All we can say about alpha is it's somewhere between 3/2 pi and 2 pi, but I don't know exactly how many radians. I would have to go around the unit circle to get the ordered pair whose coordinates would be 24 comma -7. That would be the point 24 -7 right there. All right, this is an idea that we're going to use a lot in the next few days, and a few days is all we have left. But during that time, you're going to hear me say over and over, I don't know exactly what alpha is, but I can draw a picture of it. Or I don't know what beta is, but I can draw a picture of it. Before we go on to 24, does anybody have a question? I guess, Evan, that would be you. Do you have a question about number 18?
No, not really.
Okay.
If you want to wait a second, I'm sure if they have a question, they'll type it out.
Man, I don't know why they don't use Remind. They're chatting with you in some app that I don't have.
No, it's on Zoom. There's a chat function.
Oh, shoot, I keep forgetting that. And I don't have, oh my goodness. I see 9. Oh, now I can't make that reappear. Okay.
I don't know about you, but on mine, it's just at the bottom.
Well, mine appeared at the top, but it went away and oh, there it is. Okay. What would I do without you? I can hear everything. I just can't get my mic working, and they're typing answers to things. Okay. I wish I'd known that a minute ago. And someone has told me before, and I just forgot that existed. All right. Well, let's go on to 24. Like number 18, I don't have any angle memorized on the unit circle whose cosecant, that's the reciprocal of sine, would give me 13/12. And I don't have any angle on the unit circle memorized whose cotangent would be 4/3. So I don't know exactly the degree or the radian measure of alpha or beta, but somehow I'm supposed to find the sine of alpha plus beta and the tangent of alpha plus beta. The only other thing that I know about alpha and beta is they're both acute angles. What's important about that? What does that tell me?
It helps you find out which quadrant they're in.
Exactly. In number 18, we needed to know what quadrant alpha was in, and number 24, we're being told that alpha and beta are both in quadrant 1. So I just need to draw a triangle with some angle alpha. Now, I didn't draw my whole Cartesian coordinate system there, but that's my y-axis and my x-axis. So I have some angle alpha, and also in the first quadrant, I have some angle beta. And I just need to label those angles in such a way that cosecant of alpha is 13/12. Now, cosecant's the reciprocal of sine. Using the words opposite, adjacent, and hypotenuse, what's the definition of sine?
Opposite over hypotenuse.
So this cosecant must be hypotenuse over opposite. In other words, the angle alpha has as its hypotenuse 13, and the side opposite alpha is 12. And 169 minus 144 is 25. Square root of 25 is 5. So 5, 12, 13 is a Pythagorean triple. For beta, I need to think cotangent, or tangent is opposite, opposite over adjacent. So cotangent is adjacent over opposite. That means the side adjacent to beta is 4, and the side opposite beta is 3, and that means the hypotenuse is 5. So without knowing what either alpha or beta are, I can still find the sine of alpha plus beta and the tangent of alpha plus beta. I need the addition formula for sine, and it is sine cosine plus cosine sine. Sine the first angle, cosine the second angle, minus sine of the second angle, cosine of the first angle. I'm going to make sure I wrote that down correctly. Sine cosine plus cosine, I'm using the addition formula. Sine cosine plus cosine sine. Sine cosine plus cosine sine. And I can read each of these 4 values straight off of these 2 triangles. What would sine of alpha be? Here's alpha. What's sine of alpha?
Sine of alpha is 12/13.
12 over 13. And what is cosine of beta?
4/5.
What is sine of beta?
3/5.
3/5. And cosine of alpha is 5/13. That's 48/65 plus 15/65 is 63/65. 48 and 15, yeah, that's 63. So it's kind of cool, if you're a nerd, kind of cool that without knowing what alpha is and without knowing what beta is, you can still find what the sine of alpha plus beta is. In the B part, we're going to do the same thing for tangent. We need the addition formula for tangent. That's tangent U plus tangent V. Tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. And I can just extract those values from my triangles. Tangent alpha would be 12/5. Tangent beta would be 3/4. One minus 12/5 times 3/4. It would be absolutely cool if you didn't have to have a calculator to figure that out. We already know 12. No, it's not the same as up here. That would be 48 and 15 is 63/20 over 1 minus 36/20 would reduce to 18/10, would reduce to 9/5. Double check that. 48 and 15 is 63. 63 over 20 divided by 4 is 9/5. Yes. (5/5) minus 9/5 is -4/5. Dividing by -4/5 is the same as multiplying by -5/4. If I haven't done something goofy, that's -63/16. Does anybody have a question?
I'm good.
All right. How could we find the quadrant containing alpha plus beta? We know that alpha and beta are both first quadrant, but their sum may not be first quadrant. For example, if I add a 60-degree angle to a 70-degree angle, 60 and 70 are both in the first quadrant, but 130 is not in the first quadrant. So how can I find, Evan, you were fixing to say something?
You could use the triangles you already have to find alpha and beta and add them together.
Well, that was kind of the whole point, though. I couldn't find alpha and beta exactly. You know, I could say...
You don't necessarily need it to be exact, since it's only asking a quadrant.
Tell me what you're thinking, Evan. I'm trying to understand.
You could use the triangles to find out alpha and beta. It'll only be like an estimation of alpha and beta.
Oh, okay. And tell me how I would do that. You're right, I could do it, but how could I find alpha from that triangle?
Using like sine and cosine and stuff.
You're very, very close. How could I use sine to find what alpha is? I could say sine alpha.
Sine inverse.
Inverse sine. Yes, yes, yes. Okay, so that actually wasn't what I was thinking, but it would work. You could say alpha is the inverse sine of 12/13, and beta is inverse sine of 3/5. You could do that and then add those two numbers together. What I was thinking about is if sine is positive, then it has to be in quadrant 1 or 2. If Q1 or 2, if tangent is negative, what two quadrants is tangent negative?
1 and 3?
Yes, where you have a positive divided by a negative or a negative, not 1 or 3. That's where tangent is positive.
Oh, yeah, sorry, 2 or 4.
Okay, tangent's negative in either 2 or 4. So what quadrant does alpha plus beta have to be if sine is positive and tangent is negative?
2.
Yeah. But I like the way that you thought of that too, just using decimal approximations. If this turned out to be, alpha turned out to be, say, 60 degrees and beta is 70 degrees, then 60 plus 70, 130 degrees is in quadrant 2. All right, officially we're 1 minute over. I just want to show you one thing to tell you how easy these 4 proofs are going to be. I just want to do one of them. We'll do number 30, and it'll be the easiest proofs you've ever done. Remember, when you're doing a proof, you have to start with one side and work on it till it becomes the other. When you see sine of x plus pi over 2, what formula pops in your head? And I'm just asking for the name of the formula.
addition of sine formula.
Addition formula for sine.
Addition.
And the addition formula for sine is sine cosine plus cosine sine. Sine of x cosine pi over 2 plus cosine x sine of pi over 2. What's cosine of pi over 2? The x coordinate at pi over 2 radians. Pi over 2 is right there. What's the ordered pair?
0. Sorry, I was muted and I didn't notice.
You answered me 3 times. I'm sorry. That's okay. That's the order pair 0, 1. So cosine is 0 and sine is 1. What does that all boil down to?
That's just 1. No, what? I don't know where I got 1.
The first term is 0. The second term is cosine x. So 0 plus cosine x is just cosine x. And really, we just proved one of the cofunction formulas. Whatever we said, whatever sine is, or let's say it the other way, whatever cosine is at x radians, sine's going to be the same thing, 90 degrees or pi over 2 radians from there. So those last 3 formulas, you just need to figure out which addition or subtraction formula you need. 32, you need the subtraction formula for sine. 42, you need the addition formula for cosine. And 44, you need the subtraction formula for tangent. And those proofs will fall right out. Okie dokie. The homework is these problems. And I will be able to Zoom tomorrow. So there is no video for 6.4 for you to watch in advance, but do this 6.3 homework and then I'll record 6.4 as we're going over it tomorrow. Okie dokie.
All right.
All right. Y'all have a good day. See you tomorrow.
See you tomorrow.